So the norm is not like we know with one sun.
The fauna, the different types of planets, different scenarios to form a solar system or planetary system, it's not as simple as we thought. It's a lot of different things. So that's one technique, the transit, and a lot of planets also have been detected indirectly by spectroscopy. So looking at the shift of the spectrum of the star itself due to the presence of an exoplanet or several planets. And
so you're saying that exoplanet being there somehow shifts the light from that star?
Exactly. So that's called radial velocity technique, because one looks at the high resolution spectrum of a star, and the way it is disturbed, it means that there is some kind of mass orbiting there and there with such and such inclination and different parameters. And with this technique, we found systems that look a little bit more like our own. And sometimes planets are confirmed with different techniques. And then there are planets detected by micro-gravitational effects, which are called micro-lensing. So this is Einstein theory. The light is deflected by mass, by some massive star, and so you can detect basically small light pearls when there is presence of a planet. So there are just a few systems detected like this, but this technique is powerful because people have actually found some lonely planet, some planet that didn't belong apparently to any star, free floating planets.
Wow.
So that's new. That's a new thing. And the technique that interests me most, and that's not really the technique that allows to detect, but rather the technique that allows to characterize, is the direct imaging. So basically one is using a telescope with the best angular resolution techniques and instruments to try to resolve the planets themselves, to image directly the photons of the planets.
Wow.
And that's what we are doing with the instrument I'm in charge of at ESO and in other instruments in the world. So far, just a handful of planets have been imaged directly. And these ones, so far, they are very big Jupiters.
So, of all of those different techniques that you use to discover planets, of those 1,000 exoplanets that we've discovered, which technique finds the most?
The techniques that find the most right now, exoplanets, is, I don't know if it's transit or radial velocity. It's one of those. Those techniques have found hundreds of planets. And there are new instruments coming, or new space missions that publish 50 planets at a time, 100 at a time. They don't advertise one planet at a time. They wait to get like a bunch of interesting ones, and then they make a nice release. So these are the most prolific techniques, let's say, but the planets, they are really either fast orbiting, either massive, either they cannot be confirmed. So there is a lot of work after those detections, let's say, to find which systems are interesting.
Because those techniques, those two that you just mentioned, rely on the planets passing directly between the Earth and that star, does that mean that we discover only those planets as opposed to ones that might be orbiting up and down to the star relative to the Earth?
Once you discover a planet that's transiting, so you have the star, you have the planet in front of it, and then we ourselves in Earth, and we see a drop in the light curve. Well, sometimes if you find something interesting, you can wait until the planet goes also behind the star, and that's a different technique, because then you can do in-transit and out-of-transit spectrum, for example, and you can sort of detect or indirectly derive the atmosphere spectrum of the planet, which is absorbed by the... Well, it's a bit more complicated than this. You look at the spectrum of the star, and you look at the spectrum of the star plus the planet, and then you try to wrest one from the other. And that's when the planet is behind, it's basically a secondary transit, it's called, or an eclipse.
Whereabouts are these exoplanets? Are they all kind of around the Earth, or are they in other galaxies, or are they kind of clustered around our galactic center maybe?
So far, we don't have the power to find exoplanets in other galaxies, because basically the exoplanet science in general is a galactic science, let's say, because we study other galaxies, but we don't have the resolution power or a single star in a different galaxy than our own is actually too faint and too unresolved to provide information like this, let's say. So all the exoplanets we have found so far are in the Milky Way, and they're actually quite close in the Milky Way, because the closer, the easier to characterize, and the brighter the star are for a given type of star. So they're basically quite close, and they orbit different kinds of stars. And for direct imaging, they tend to be orbiting young stars, but that's not really because there are no planets around old stars. It's just because it's easier to find planets around the young stars, because the brightness ratio between the star and the planet is actually there's a smaller difference actually between star and planets for young stars, so it's easier to image them directly. For the other techniques, they are found around a lot of different kinds of stars, let's say. And a solar system as evolved as our own, this would be very difficult to detect, because the planets are very faint compared to the sun. And the disk that all the planets are more or less in the same plane, and they used to be a disk, it's basically very diluted now. So it's very difficult to really find such a system. But we found systems that may be like our own, but a couple billion years younger, let's say.
What it's about the current progress in space exploration that makes us willing to celebrate the World Space Week?
As an astronomer, everybody is hoping for the James Webb Space Telescope, this 6.5 meter telescope that will operate in the infrared, and which is going to be basically the Hubble of the new generation, the biggest telescope in space for us. But right now, this project is kind of in balance. So we're hoping for that, and there are tons of little other missions. I'm saying little missions, but there are no little space missions. They're all very big missions. And so telescopes, now they are actually foreseeing telescopes which are going to be of rather reasonable size, of 1.5 meter, things like this, dedicated for exoplanets, for example. So to detect them also by astrometry, looking at the movement of the star directly. The star movement and proper motion is disturbed by the presence of some body. That's another technique. There will be some kind of missions like this. But astronomers are interested in space in general, let's say. But even though we don't work directly with spatial means, everything we do from the ground has to do with other things that have been detected from space, and vice versa. There is a great synergy between the two fields. The World Space Week for us, it's a great opportunity to try to find synergies between ground-based astronomy and space-based astronomy, between the public interest for space and the public interest for astronomy.
Wicked. So do planet-based telescopes actually have a future, or do you think eventually we'll do all our observing from space telescopes?
They have the ground-based facility have a future, because basically they are very complementary with space-based facilities. It's very, very expensive to send something in space. Currently, we have the Hubble Space Telescope, which is 2.4 meter, and it's aging, and it was a revolution basically in astronomy, and provided the sharpest images ever, the deepest images ever, and so on. But from the ground, we are building facilities that could not be sent in space. In some cases, they can be sharper. In some cases, they can be deeper. So the atmosphere, of course, is providing some kind of twinkling of the images, but it's also absorbing some bands. We cannot see all the wavelengths we would like to see from Earth, whereas from space, basically everything is possible. So from the ground, with less money, we can build a much bigger telescope than from space. So for some applications, it's actually worth it. And I would say that from one space mission, tens and tens of telescopes are built on the Earth. So really the two community, sometimes it's the same. Some people work as well with a space-based telescope, and other with ground-based telescopes. And in the future, as the facilities become bigger and bigger, the community tends to use both, really, and different kinds of observations in different bands and wavelengths.
So, on a bit more of a kind of personal question, you must have seen all sorts of incredible things from your work. Is there any one image that really stands out for you? One thing that you've seen that made everything, all the sleepless nights, worthwhile?
One incredible thing I've seen working at the observatory, while being in the south of the southern hemisphere, we tend to have the big customers, the Galactic Center team. So they monitor the Galactic Center stellar motions since many years, and they look at the movement of stars. They look at the movement of stars located very close to the central black hole of the Milky Way and how they move. And they can determine the mass of our own black hole and properties. And sometimes, actually a couple times a week, more or less, some stars or some matter falls into the black hole and a flare is observable.
I thought that our black hole was quite stable. This is what I was told. Now, should I worry?
Well, no, it's quite stable, but it's still swallowing some matter, let's say. and so that actually I witnessed Galactic Center flare a couple times. That's about 6 months of the year when the Galactic Center people observe, and sometimes we observe without them, with a couple instruments, a spot that's empty and it becomes bright for a few minutes, let's say, and then it goes empty again, and that means that something fell on the black hole. And of course it's not real time because it's very far away. Mm-hmm. So it's not real time, but when it happened it was real time, so it's kind of